Professor Qi Dou. She was part of the Future AI Consortium. She is actively working on guidelines. As you know, this was made by many different types of stakeholders working together, and she brings the perspective of clinicians, of surgical robotics, and a lot of very interesting perspective. Before we start, I just want to do a little bit of housekeeping. This is an interactive chat. We want to have Q&As, please, in the chat, but also feel free to jump in and ask the question yourself. I'm happy also to read the questions for you. I will be taking today the role of Karim because he's not available. And my name is Laura Arbeláez, and I'm the AI ethicist of the lab. The webinar will be recorded and available afterwards. So if you don't want to be on camera, just simply don't put your camera or don't put your voice if that's not what you want. And the talk duration will be 30 minutes, and then we will have the Q&A session. There will be following future webinars, possibly after the summer, and you will receive the information, or just can follow our website as well. And now just a quick introduction to our very interesting presenter. She is Professor Qi Dou. She's an assistant professor at the University of Hong Kong, the Chinese University of Hong Kong. She's an affiliated member of the Robotics Institute of the Medical Intelligence and XR Institute, the Multi-Scale Medical Robotics Centers, and the Hong Kong Center for Logistic Robotics. So she has a lot of experience and she has a lot to tell us about it, and we have a lot to learn. So we welcome her, please. And yeah, many thanks to everyone who is joining. Thank you.
Okay, thank you. Thank you very much, Laura, for the nice and kind introduction. So let me share my screen. Can you see my screen properly?
Yes.
Okay, all right. Okay, so thank you very much for the invitation. And I'm very glad to be here today and as part of the course or in the Future AI, and now I'm presenting some of our recent work in the Future AI webinar. So my topic today will be about a step for AI copilot in robotic surgery. So as we know, currently the AI-powered robot is basically transforming many different application areas, and such as the warehouse automation in the ordinary factories, and robot taxi and human robot for doing many housekeeping and daily tasks. And those robots are basically powered by artificial intelligence or embodied intelligence techniques, which is a combination of computer vision, robot learning, and reinforcement learning and robot manipulation tasks. And in the opportunities of healthcare, so basically the AI plus robotics in healthcare application has vast potential and a sector impact. One of the reasons is due to the challenge of aging and health. So basically, currently, all the countries worldwide are faced with major challenges of aging due to the statistics from World Health Organization. So the WHO reported that according to statistics, between the year 2015 to the 2050, so the proportion of the world's population, so-called aging population with age over 80 years old, will be nearly doubled to the mid of this century. And that means basically by 2030, so which is I think around 5 years later, 1 in 6 people in the world will be aged 60 years or even older. So that is a huge challenge, and we do need a lot of machine that in the healthcare field, that either in the hospitals or in our daily life, to assist people, healthy people, to address this challenge from taking care of the elderly, taking care of the patients. So then that is an urgent need for more accessible healthcare through automation and through AI-powered machines, and to achieve better equality through AI tools. So basically for the robot, there are different kinds of robots for healthcare. The most well-known one, or basically I think we are most familiarized one, is the Da Vinci robot, which is for minimally invasive surgery and currently widely used in clinical practice. It's being performing millions of minimally invasive surgery worldwide every year. And there are other types of robots also being developed worldwide, such as the exoskeleton and carrying robot in the home environment, and in some nano robots in the micro robot, etc. So there are different types of mechanical design and also the application scenarios for the robot in healthcare. So for the AI plus healthcare robot or AI plus medical robot, there are some progress is already happening in the field. And one of the examples is doing the navigation, so which is very similar to you navigate a human robot in your home, say going from living room to the bedroom, and then you have a path. So similarly, for the medical robot, such as here, this work that we have done is to use AI to do the navigation and path planning for a macro robot. So that, if, for example, if you are placing your macro robot swarms into say a blood vessel or tubed anatomical structure, say from this position, for example, go to this position, and then we can use AI to automatically doing the planning for the path and also automatically compute the shape of the macro robots to do self-configuration of change the shape of itself to going through the pathways. And similarly for the minimally invasive surgery, so this kind of robot navigation-based and recognition-based tasks can also be conducted. For example, we could use computer vision algorithm to recognize the safe and dangerous stones of the endoscopic images, such as in this example, so can recognize in the endoscopic submucosal dissection, which is a curable therapy for the early stage GI cancers. And the clinical need is to differentiate the muscle area and submucosal area so that you can doing the dissection within the submucosal area and avoiding to cut into the muscle area to avoid bleeding. And then there are many kinds of computer algorithms, and such as here, the one that we propose is to use the uncertainty estimation that is trained with the fine-grained reward maximization, which is the reinforcement learning way for updating the model with a policy gradient to do the segmentation and uncertainty estimation in the same network. So this is the recognition, and then based on that, you can recognize what is the danger zone, such as the red areas marked in the scene and the safe zone marked in the blue and green areas. And furthermore, we can do the path planning, that is trajectory prediction. So basically here you can, based on the image and based on the recognition of the safe and dangerous zones, then you can do the trajectory that is being predicted automatically for suggesting and indicating the dissection trajectory. And this kind of technique is being trained by using learning from human demonstration. So that is when collect the video data and then do the labeling of the trajectories step by step in a line, and then we can use the such and different policies to doing the distribution mapping of the input image to the output distribution for the descent trajectories. And this technology currently can achieve a real-time prediction at around 30 FPS in real time for deployment. So here is some details for the method. So basically, we can formulate the dissection trajectory prediction task by making use of optimal policy that is input in the image. That is basically you can have the state representation for the images, and then the output is the action prediction, so which is a series of 2D coordinates on the images. And then the demonstrations are being given by expert operation videos. And then the idea is to doing the different policy learning to regress and to learn the implicit policy that is basically mapping the state input to the action output. So then to date, I think most of the cases that we have done that people can achieve is basically, I think navigation is a task that has been relatively better solved compared with another task, which is so-called manipulation. So for manipulation, that not only just to give a trajectory in a relatively larger space, but the manipulation requires to do the fine-grained manipulation and doing the deformations of the tissues in a confined space, and that requires the interactions between the instrument and the tissues, and then that also need to control some of the dynamic situations in the scene. So for navigation, most of the cases that is relatively a larger motion space, and then you are not necessary to have too much interaction with the surroundings, but manipulation is relatively challenging task. And currently in the general robotics community, so a lot of work is going on by making use of the robot learning for manipulations. And one of the methods is to use so-called embodied AI, that is to learn the policy in the simulation platform. Then the simulator can generate different objects, different relative positions of object and the robot arm, and different appearances of the scene, such as this. They can change the textures, the colors of the kitchen, and have the robot to doing the adaptation learning in the simulation. And this kind of simulator help a lot for the policy learning in terms of manipulation and some other robot control tasks. And the challenge here for the robot learning or robot surgery learning, surgical robot learning is in the first place is the lack of the simulation infrastructure in the field, in the community. So that make a little bit lagging behind for this robot learning community to compare with the general robot learning community. But in fact, people have already made some efforts in the field. I think back to around 5 to 6 years ago, they are already emerging this kind of simulation platform, which is using exactly the same idea and concept as the general robot learning communities, such as some representative simulators here as I listed here, including the DVRL, which is proposed by UCSD. That is one of the first digital twin of the simulation system for the Daphne Research Kit platform. And AMBF is one developed by GQ by making use of the physical-based simulation for doing the instrument and the tissue interactions, etc. And also for this one is Unity Flex ML is developed by University of Verona, Italy. Then the key idea for this simulator is to build the soft object simulation scenarios, basically soft tissue simulation interactions in the with the Unity and Flex ML. So those are the early pioneer ones. And very recently, there are a lot more for this type of simulators, such as the Surgeon Gym. And for the soft body simulation, NVIDIA is also making efforts to make some soft body object inside their ASIC Gym simulation platform. And they are also putting efforts to support the medical robotics field to doing incorporating some asserts or 3D objects in the NVIDIA simulation platform. So we can already feel that have a feeling that the community is growing and more infrastructures are being provided to facilitate the research in this field. And for us, we also did our own effort to contribute to the infrastructure development. And the one that we developed is so-called Thorough, that is for the purpose of surgical robot learning. So this one that the simulator platform, the Thorough, it has two characteristics. One is that it is reinforcement learning center. So basically that is different from previous surgical robot simulations such as VRAP. We emphasize more on supporting the reinforcement algorithms to acquire state in the simulation and then do the reinforcement learning, policy learning update, and actions can be updated iteratively in the simulation platform. And another characteristic is a digital twin for the DaVinci Research Kit. So the 3D models and the kinematics in the simulation is made consistent between the simulator and the hardware platform, so that the motion patterns and trajectories that is being collected or that is being learned in the simulation platform can be easily replicated or deployed in the real-world robot platform. So for this simulator, we have already open sourced it in the year 2021 with the paper, Arrow's paper, and that has been incorporated into the DVRK software ecosystem and recognize the machine learning resource there. So it currently is being adopted by research institutions such as Imperial College, London, and Hopkins and UCL and Shanghai Jiao Tong University, etc. So they are being also actively updating the simulator and adapting the simulator to their own needs for research purposes in the robot automations. So the infrastructure design of this simulation platform mainly includes three parts. The first part is the intelligence policy learning, which is the one that I emphasized just now. It's reinforcement learning centered, and we have built up the state-of-the-art library for the latest and our own developed reinforcement learning algorithms into the policy learning library, and we also open source the models that is trained for RL for the deployment in the dataset. And another one is human interaction devices. So that is to collect the human manipulation data for policy training and robot learning. And the infrastructure-wise, that is a virtual environment, include the visualization engine, physics-based simulation, and surgical task, etc. So the overall thing is developed by ourselves from the scratch. So that is basically from the very underlying simulation engine, physics engine, and reinforcement learning policies and libraries are being integrated from the very beginning. So currently, we can support the different number of tasks in the simulation platform, such as surgical skill training tasks like the pick up the needle, pick up the gauze, pick up place, pack transfer, and needle handling, etc. Those surgical training tasks are standard tasks, and we are making it by referring to the surgical skill training curriculum for the Da Vinci robot. So those are not tasks that are invented by ourselves. So those are in fact the existing tasks that is being used basically for the practice of surgeon training. And we just replicate them in the simulation platform. Now we have two versions of human in the loop interface. One is call it as a low-cost device that is using 3D touch. Basically, you can download our simulation platform from GitHub, and then we have the API from the connecting the simulator to the 3D touch also being open sourced. So you can, if you in locally you have your lab owns 3D touch, then you can easily connect your own touch to the simulation platform and start to get data from the simulation. And we also have a domain-specific device for the DVRK manipulator that is being connected from the 3 degree of freedom manipulator in the DRK MTM to the simulator for the manipulation. So this type of mapping is replicating the human manipulation style that is the same as the Da Vinci robot or similar to the style manipulation in clinical setting. So based on this infrastructure, we could support the investigation of various reinforcement learning algorithms, as it is what people can do to develop the reinforcement learning in the general robotics community or in the general robotics, the simulation platform. So they can design the demonstration guided reinforcement learning algorithms in the simulation, so you can collect the expert demonstration data as imitation and plus reinforcement learnings inside the simulator for trial and errors to explore the best policies or the optimized policies in the simulation platform. And you can also study the skill chaining for longer horizon tasks. So that is, for example, if you have a relatively more complex task and then can decompose the task from several smaller subtasks, and each subtask can be learned separated, and you have a higher level policy to doing the skill chaining for the subtask to complete a longer task, longer term task, such as this is example of the pack transfer. You first lift up the pack from one hand and you hand it over to the other hand, and then you place that to another position with the second hand. And can you also learn the policies for multiple tasks together, such as this one, we develop a decision transformer for cross-task learning, that the policy can be trained on 10 different tasks simultaneously, and then we have a testing head for each individual task to enhance the capacity of the decision transformer for the policy learnings. So this is type of offline learning method. And overall, for these different tasks, then we also build up a benchmark based on the simulation platform, so that people can download the training data set and also the pre-trained models for these replicated and implemented state-of-art reinforcement learning algorithms, including the state-based ones and also the vision-based ones. So for state-based ones and vision-based ones, the difference is that the input to the policy depends on whether you use a raw image or you use the position state of the object. So if we use the for example, the XYZ position orientation state representation as the input to the policy, then that is so-called state-based policy. You can get the states directly in the simulation in the simulator for the parameter reading. And vision-based means we use the raw image, that is a 2D RGB image or RGB stereo image on the right eye and the left eye, and then you can have the policy directly learned from the images. So in the simulator, we are doing efforts to incorporate soft body simulation for the purpose of the surgical or more surgical oriented tasks, except besides those game-based skill training tasks. And the one currently we are incorporating into the simulation is the idea of MPM, material point method, which is a classic and state-of-the-art efficient physics-based simulation algorithm. So we choose that because it can allow fast simulation and computation efficiency in real time for the frequent interactions between the tissue and the instrument. Basically, you can also change the physical properties such as the stiffness of the simulated tissue, and then we can observe different reactions based on the interaction and physics parameter settings. And similarly, an alternative that we are also considering for the generative scenes for soft body simulation. So that is basically not exactly currently the generative AIs where you are generating something from a random distribution, but for here the generation is generating a 3D image from the stereo 2D images. So it's generating simulation data from real data. Okay, so that is it's kind of concept from real to sim. The real thing is the stereo videos. So that is captured from the clinical videos from right and left eyes from camera. And then we have the stereo 3D reconstruct algorithm to recover the 3D geometries and also textures of the scenes for the simulation purpose. So for this things, and we can have different methods. Previously that we use the neural render methods to doing the reconstruction, and we can have the 3D point clouds from the reconstructed scenes, and then you can use computer graphics algorithms to doing the to convert the point cloud surfaces into the 3D textured meshes, and then we can doing the rasterization to doing the rendering for the images and use FEM methods to do the simulation. And the recent methods is to rely on the Gaussian splatting for the 3D Gaussian representation to do the reconstruction. And the advantage of the Gaussian representation is basically it can be incorporated into the MPM solver, and each Gaussian can be regarded as each 3D Gaussian can be regarded as one of the unit in the MPM solver, and you can do in the editing for the Gaussians, and then that basically interaction can be computed in the MPM for doing physics-based deformations. And in this way, you can incorporate the reconstruction and MPM-based simulation together as a complete data-driven pipeline for scene simulation that we call it as Sim Indo.js. So basically here, then you can have the simulation for various surgical scenes by just changing the input data, and they can correspondingly to generate the scenes. And in the generated scene, we can apply the forces into different positions. Basically, in the whole reconstruction, you can apply the force in arbitrary areas, and then the scene will give feedback based on the NPM computation for the visualization property of the soft tissue, soft interactions. And these motions, and you can see in this video, is completely simulated. So that is fake. And then we are simulating the scenes by generating the complete scene from these two real data and create this virtual environment, and then do the interactions in this virtual environment for the purpose of robot learning. So we can incorporate the reconstructed scene and 3D Gaussian representation with NPM into the simulation platform, as I introduced just now, like in this format. Basically, we can have the textured one in the scenes inside the simulator for doing the policy training. So with that, we can create a embodied AI-driven framework using the simulation platform and sim to real transfer. Basically, it is zero-shot sim to real transfer to enable the generalized surgical task automation that can be applied to different types of tasks and different scenarios. So the idea of the AI framework is a hybrid framework that incorporates visual parsing, perceptual regression, policy learning, and classic visual solving controllers. So the idea would be like this way. So we get the endoscopic images from the robotic endoscope. So that is a raw input for the stereo images. And then we have the vision foundation models, such as the segment aliasing or faster sum and depth estimation models in real time. And those basically can doing the perception for the scenes that can give the position and segmented mask and orientation and the relative distance or absolute distance between the target object and the instrument grippers in this visual passing section. And then the depth estimation results and segmentation map can be further forwarded to a multi-layer perception, which is a perceptual regressor that gives the state representation of the input scenes. So that basically gives the XYZ position and orientation or pose information of the target object that is being particularly or explicitly modeling of the state of the target object that is being used for further robot manipulation purpose in the policy learning component. And then in the third part is basically you can use the state input, and then you can do the policy learning inside the simulation platform to doing the reinforcement learning based action prediction. And this basically in the simulation platform, you can change the background and change the appearances of tissues for simulating different data to do the trainings. And the policy is to output the actions of the end effector, which gives the trajectory of the end effector of the surgical instrument to move forward or move toward approaching to the target object. So when the instrument is close enough to the target object, then we change that last step manipulation into a classic visual solving controller to ensure accurate and to ensure the precise and safe manipulation for the last step action, such as doing the grasping for the needle. So overall, this framework is the pure image-based automation. So it's like the style of basically you only use the standard endoscope from the clinical viable robot platform, and then it can give you the output actions directly without using any extra sensors or any additional setups. So no other things beyond or more than the clinical settings. So with this platform, we can do a generalized task automation framework. So that can be applied to the simulation, to the dummy research kit in the ex vivo lab-based tasks, and in the ex vivo settings, and also in the in vivo settings, using the same pipeline, using the same framework. So that is, we are minimizing the task-specific and scenario-specific engineerings for surgical task automation. So which is advanced than previous traditional control methods or control-based pipelines for the task automations. So we have automated a number of assistive tasks, including the manipulation of the endoscope camera and grasping the needle, grasp of the gauze and tissue retraction and blood vessel clippings. We set up the experiment on the robot platform, which is a clinical viable surgical robot platform developed by industry collaborator Colossus Robotics. And we have deployed our AI onto their surgical system. So here is the success rate for these 5 different tasks. And this plot is the length of robot execute trajectory to evaluate the economy of the trajectory lines being predicted by the reinforcement learning policies. So here is the ex vivo experimental demo that we have tested the 5 different tasks in a wide variety of scenario settings to test whether that is generalizable in the complex scenes. So the first task is to doing the control of the robot endoscope views based on the position of the instrument. So the goal is to put the position of the instrument into the middle of the image by moving the orientation of the endoscope. So the model can be robust to the different changes in the scene. And the second task is needle grasping. That is, you use the grasper to pick up the needle. We can have variations in the size of the needles, in the changing of the brightness, and enter some cluster in the scene. And the third one is gauze picking. So we can handle the variance of the gauzes with different positions in the scene and different volumes of the blood in the scene, and then can do the different brightness, and then basically the for the picking and placing the gauze, or the 2 steps are basically automatically conducted by the AI through doing the scene perception and then doing the depth estimation and execute the learned policy. So those learned policies are being directly deployed to the platform. So this is a simulation for the ex vivo study for the soft tissue retraction. So this hand, okay, this arm is AI controlled, automatically controlled, and this arm is human controlled. So we are replicating the scenario of human-robot collaboration, that you use your assistive hand to lift up the tissue and then doing the cutting. And this task is so-called blood vessel clipping. That is, you place clippers onto the blood areas, regardless of the thickness of the blood and the appearances of blood, and you can also continuously put multiple clip on the same blood vessels. And we also conducted a in vivo experiment for this framework. Again, thanks to the generality of the framework and its powerfulness of zero-shot sim to real transfer. So we can execute the learned policy in the in vivo scene, which is completely unseen before by the AI models. So here are the results. Basically, in the real time, you can do the image is being perceived with visual perception for the segmentation and for the depth estimation of the scenes. So here we can do the gauze picking. In the in vivo setting, you can still see the breathing of the. This is a lab pick for the stomach dissection simulated procedure. And then the system can do the soft tissue retraction as well. So that is basically can doing the automatic lifting up for the tissue areas, regardless of the high brightness and low brightness. And also it also create similarly for the human robot collaboration scenario that you have your third hand to doing the lifting and the two hands being controlled by humans to do the more dangerous tasks such as the dissections. And for the blood vessel, again, we have three arms together. This arm is automatic one that is doing the clipping, and these two arms are human controlled one that you can hold up the vessel and then use your third AI automated arm to place the gripper for you. Usually this gripper is being placed by a surgeon assistant. So it's another assistant for helping do the task, and you can basically relieve a little bit for the workload for the assistant. So now I think currently the surgical robot automation or the blueprint of the AI copilot for the robotic surgical scenario is coming. So that is basically much closer than with us than we expected before. So basically it would come much sooner than people expect. So the next step is to move forward from the simple task to more complex tasks, that is more longer horizon tasks. So currently we are around here for the from robot assistant and to task autonomy, individual task autonomy. And then we are moving forward is for the conditional autonomy, also called step autonomy. So that is basically extending the time horizon for the automated part. Still, the duration is being conducted by human-robot collaboration, just you have your AI automated robot arm to assisting humans in a relatively longer time period or time or very relative longer time horizons for doing the human AI and robot collaboration. So now basically you have the lot of data basically in the surgical robotics field. I think that is basically our data is higher quality and much more compared with the general robotics community. Currently, the general robot community, such as the human robot, and some like the grasping and object manipulation tasks, they are collecting, make a lot of efforts to collect the data with some specific setups. But in surgical robot, naturally, every day in every surgery, those data are being recorded routinely by default, including the video data and including the robot motion data with the teleoperation system. And this teleoperation system have a very high precision that is in a millimeter level, and it has a very good standard of synchronization between the manipulator video and also the motion from the patient side. So that is basically the motion here and the motion here, and the image inside the console are being very well synthesized with high quality. So this kind of multimodal data can be incorporated together to learn how to conduct the automation and also to learn basically the skill assessment and skill learnings. And this kind of multimodal data have already been explored before, and the previous work has evidenced that those combination for the visual and kinematics data can facilitate recognition and understanding or analyzing of the surgical procedures. And this data basically, as I said, so it is routinely recorded in every single procedure. And as I said in the beginning of my talks, currently each year, this robot is doing millions of patients for minimally surgery, and this particular number is also increasing dramatically with the increasing speed around, I think at least 10% every year more for the current increasing popularity of surgical robotics. So we do have a lot of potential resources for data which are not yet being well explored by the community yet. But I think we do have there is a huge hope for for moving forward with the joint efforts in the field. And for the algorithm wise, there are also some advanced and new ideas and also we can borrow and inspired by the robot learning community, such as using the vision language models or the VLA, which is very hot now. That is, you use the image and input and use the language model to doing the high level planning, and then you use the predictor to do the action predictions. And those are the parts that is not yet being explored by the surgical robotics community so far. So basically, we have just initially tried we at least currently we found that it's learnable. But how to learn it better and how to make it being able to reach the level of precision that is needed in the robotic surgery is still pending to be explored with various challenges that is basically being presented there, such as the task complexity variances and safety considerations and lack of the depth sensor. You can only rely on your stereo images to estimate the scenes. So here is a quick summary that is for the techniques that are applicable and effective for the surgical robot, and domain-specific efforts are very important, and people are keeping working hard in this field and keeping open source and building up the community of bringing more people in. And the AI Copilot in robotic surgery is a very good field, and that is very well aligned with the technical pathway and the clear impact that is either regarding the general robotics community or the future AI healthcare community, etc. So that part is also have a potential to bring a new round of service for the patients that has never been enjoyed before. So this is the end of my presentation, and we have openings, and very welcome to contact me if you are interested. Thank you very much.